Hello again everyone, today we're going to look at chapter 19.7, stellar luminosity, and within today's lesson we need to look at Wien's displacement law, and then we'll move on to talking a little bit more about luminosity. We've mentioned luminosity before, but we need to apply it into the form of an equation and using Stefans constant, and then we're going to use Wien's displacement law and what then is called Stefans law to estimate the radius of a star. I've just played back to make sure the sound is working, and star, a bit excited, my apologies. We'll carry on in my dulcet tones. If any of you have ever studied resistant materials or seen a metal in a fire, it will obviously heat up and it will change colour. It will glow yellowy orange as it changes to different temperatures and maybe move towards a really white colour when it's really hot. And blacksmiths use colour to decide if the material is at the right temperature so it can be shaped. And likewise we can use that idea of temperature and colour being very much linked when looking at stars. And the first thing we'll look at is blackbody radiation. I've written out the definition here of what a blackbody is, just taken from your book. The first thing to point out is it doesn't really exist. There is no such thing as a blackbody. It is very much idealistic. But what it is supposed to do is absorb absolutely everything. So it absorbs all of the electromagnetic radiation that goes towards it. And then, assuming it's in thermal equilibrium, it will emit a certain wavelength based on certain temperatures. So when you have a certain temperature, it will give off a wavelength of energy. And you've seen before the idea of E equals HF or HC over lambda, where energy, in this case temperature, well heat, is then very much linked to frequency or wavelength. This is the sort of diagram that you may see if you type in blackbody intensity wavelength graph into Google. If we focus just on one of the lines, let's just focus on this line just here for now and ignore all the rest. What it is a diagram or graph of something that's at 5,000 kelvins, so very hot. And the object doesn't just release one wavelength of colour, it releases a spectrum of wavelengths. And the area underneath the graph represents the quantity of that particular wavelength. So when we've got a long wavelength, it gives off a small amount. Likewise, a short wavelength, it gives off a small amount. But it gets to a point where you get to a peak, and that's called lambda max. And that's the most colour, in this case, that is given off. So you would see something that's 5,000 degrees Celsius as roughly a red colour. Let's now look at the coldest one on this example, so the 3,000 Kelvin object. So this one might give off a tiny bit of colour as it's heated up, but the bulk of the energy that's given off is to the red end of the spectrum, so infrared. So actually something that's 3,000 Kelvin wouldn't really emit any light. And if we think about your oven at home, for example, that might reach a temperature of maybe, say, 500 kelvins. So if we're looking at 500 kelvins, we would have a graph that looks something like this. And if you notice, your oven doesn't give off any colour unless you have the light on. But assuming you have the light off, when you turn your oven on and it's at 500 Kelvin, it's not warm enough or hot enough to release or give off any visible colour. However, we do know that there's lots of infrared because it cooks our food. Now if we look at the other extreme, and let's go for this one just here, the one at 6,000 kelvins. This time lambda max, or the peak wavelength, is somewhere in the yellow region, and that would give off lots of the colours. There'd be some ultraviolet light given off and lots of infrared. But because the bulk of this and where the peak is in the visible region, then something at 6,000 Kelvin would give off an awful lot of colour. And it just so happens that our sun is just under 6,000 degrees Kelvin, and when we look at our sun, we do see all of those colours, because if you have a prism, as we saw a couple of lessons ago, it gives out the rainbow of colours. But it certainly has a main colour when it merges together of a yellowy orange colour when we look at it, without the light being spread out or separated. But anyway, the key point with this is as you get hotter, the maximum peak of the graph tends to shift to the left. Or, conversely, as you get cooler, the peak wavelength gets longer. So before we move on, so at any temperature, radiation gets emitted. And equally, we do know that because when we look at ourselves in an infrared camera, it shows us that we as humans give off infrared radiation. So anything with a temperature gives off some form of radiation. And likewise, different wavelengths have different intensities. So you have different amounts. Blackbody radiation, as I mentioned, an idealised object, doesn't really exist, but we can use that as an idea to help explain other things. And what we use the idea of a black body to do is link the temperature of something to the wavelength at a particular temperature. There's a useful website to help explain this, and a chance for you to play around and change different temperatures, and that's PHET, P-H-E-T. So all I've done here is I searched for black body spectrum and then typed in the word PHET, and then this page appeared. Click on the play, or you can download it if you're super keen, but on most computers the play function will work, and you'll get this come up just here. And what you'll be able to see is if you move this up and down, the peak will change. Now in some cases you might need to zoom in or zoom out, because as you get hotter the intensity gets a lot larger. It also gives you an indication here about the colour that it is given off. So notice the colour when you're at a light bulb, and then when you go down to the temperature of the Earth, and likewise when you go to another star. We've got other things here to play around with, but the key thing is this is the visible spectrum. Up here's infrared, over here is ultraviolet, etc. And you can get a good sense of what energy or what types of radiation are emitted as you vary the temperature of an object. So let's just focus on Wien's law, which was one of the main foci of the lesson. The idea that lambda max is proportional to 1 over T. So where T is the temperature, and lambda max, that's the maximum wavelength at a given temperature. And what he said is if you multiply those two together, lambda max T, you get a constant. And that constant is then known as Wien's constant. Something to be aware of, and it might not be something that you've done much on, and that is Kelvin. So in this topic, temperature is no longer in degrees Celsius, temperature is in Kelvin. Kelvin is an absolute scale where 0 Kelvin is the coldest that you can possibly get to, and that's the equivalent of minus 273 degrees Celsius. 1 Kelvin is minus 272 degrees Celsius. The intervals between Kelvin and degrees C are the same, but the conversion is 0 kelvins equals minus 273 degrees Celsius. It might be worthwhile looking at the internet or in a book about that. We do cover it more when we look at thermal physics in a bit more detail. But for now, just be aware that the temperature should always be in Kelvin. So let's look at the graph in a bit more detail again. So as the temperature of an object increases, the peak wavelength decreases. As each line goes up, the temperature gets hotter, but the peak just moves slightly to the left. You should also notice that the peak becomes sharper. So here it's really broad. The peak's quite broad and it's quite hard to choose exactly where the peak wavelength is. As we get hotter, it becomes less broad and it becomes slightly easier to find the maximum wavelength. And this is the easiest one. You can see quite easily where the maximum wavelength is. And I've mentioned before, stars are modelled as black bodies. In other words, what they absorb, they emit, and they emit a range of different wavelengths. But by looking at the radiation that's emitted from stars, scientists can then determine how hot the surface of it is using Wien's displacement law. If they know what the peak wavelength is, they can then work out what the temperature is in Kelvin. Moving on to Stefans law, or also known as the Stefan-Boltzmann law. We saw luminosity when we looked at HR diagrams, the idea being that luminosity, you might think of it as brightness, but you've got to see it as power, how much power is emitted. So therefore, when we look at the unit for luminosity, we need to be thinking watt. So, the total power radiated per unit surface area of a black body, so how much power is given off over a certain area, is directly proportional to the fourth power of the absolute temperature of the black body. Crikey. Well, let's break that one down a little bit. So, the power is L. The surface area, so that's of a sphere, 4 pi r squared. That's our Stefan constant. And then when it mentioned the fourth power, it means t to the 4. So in other words, if you have two objects that are the same size, you can get rid of the 4 pi r squared and you can say that L is directly proportional to t to the 4. Luminosity is directly proportional to t to the power of 4, assuming that they're the same surface area. And as I've written just here, if you are reading round in different books, A is sometimes used rather than 4 pi r squared. And likewise, you could also say that L is directly proportional to r squared, or L is directly proportional to 4 pi r squared as well. So from that one equation, you can look at quite a few proportionalities. So that certainly goes through this bit, but what we haven't yet done is using Wien's displacement law and Stefan's law to estimate the radius of a star. So in your book there is a worked example. So the peak wavelength of radiation emitted by our sun is about 500 nanometers and its surface temperature 5800 Kelvin, and its luminosity is 3.85 times 10 to the 26 watts. The peak wavelength emitted by a nearby star with a luminosity 10 times that of our star is 310 nanometers, show that the radius of this star is approximately 840,000 kilometres. So it goes through two different steps, but in essence what you've got is Wien's law, where you use the temperature to then apply it into Stefan's law later. But there is a slight complication just here that we need to look at first. So the first part is to look at lambda max T of our sun. So that's the 500 nanometers times 10 to the minus 9 for nano. And then we multiply that by temperature. Now in some instances you might then get the constant that I showed you earlier for Wien's law. But because it is a constant, you can then put it equal to the other star. And then by doing that, we can work out its temperature. So we know that it's 310 nanometers, or its peak wavelength is 310 nanometers, and then multiplied by the unknown. And then we can rearrange to find the temperature of the other star as 9,355 Kelvin. For part 2, we're trying to find the radius. So we do need to rearrange the equation. So r equals the square root of L over 4 pi sigma t to the 4. It said the luminosity of the star is 10 times, 3.85 times 10 to the 26. So we can put that in just here. And then we've got some constants. And then we've got the 9355, and we need to remember to multiply it by the power of 4. And then we get an answer out in metres, and then we can convert that into kilometres. And then another example. So the Wien constant is 2.9 times 10 to the minus 3, and the Stefan constant 5.67 times 10 to the minus 8. Given that the Sun has a radius of approximately 7 times 10 to the 8 metres, and its surface temperature is 5,800 Kelvin, calculate the wavelength at which the Sun's radiation peaks, and the energy emitted per second from the Sun's surface. So press pause at this point, give it a go, look back at your notes that you've hopefully been making, and when you're ready, press play and we'll go through the answer. Okay, hopefully you've had a chance to give that a go. So find out what we know first of all. So we know lambda max is a constant, and we know that's equal to 2.9 times 10 to the minus 3. And we also know that we've got the luminosity, or the total power radiated, so energy emitted per second is another phrase for power, and then we've got the equation just there. So for A, we've got lambda T max equals 2.9 times 10 to the minus 3, and it's a case of rearranging for lambda, the wavelength, so we should get 5 times 10 to the minus 7 metres. And then for the energy emitted per second, we can then plug in some numbers. So the luminosity in a calculator 4 times 3.14 times the radius squared, which is this value here, sigma 5.67 times 10 to the minus 8, and then the temperature to the power of 4 is 5,800 to the power of 4. And that then gives you the answer of 3.95 times 10 to the 26, and our unit, watts. Okay, we're now at the end of the lesson as such, so there are some summary questions that you can have a go at. What I'd also like you to do though, please, is look at the practice questions at the end of chapter 19, because we're now at the end of the chapter and now we need to do a bit of practice. Now there are quite a few here for you to have a go at, and what I'll do is make the mark scheme available, but I'll also next lesson ask for one of those questions in so that I can have a look at it. So do all of them and be prepared next lesson to hand in the one that I asked for. Thank you for listening and see you next time.